Hello, here it is another week of fundamentals of corporate finance. And in this video, we will discuss chapter 5, which deals with interest rates. Chapter 5 deals with interest rates. So the outline for chapter 5, as you see here, we will be discussing interest rate quotes and adjustments, application, discount rates, and loans, the determinants of interest rates, and the opportunity costs of capital. The learning objectives of chapter 5 are: understand the different ways interest rates are quoted, use quoted rates to calculate loan payments and balances, know how inflation, expectations, and risk combine to determine interest rate, and also see the link between interest rates in the market and a firm's opportunity cost of capital. So the interest rate is the cost of borrowing money or the return on investment expressed as a percentage. It represents the compensation paid by a borrower to a lender for the use of funds, or the reward earned by an investor for lending or investing money. Now, interest rates can be fixed or variable, and they play they play an important role in various financial transactions, influencing borrowing costs, investment returns, and overall economic activity. The effective annual rate, or EAR, or APY, it is a financial metric that represents the annualized interest rate, and it accounts for the impact of compounding on the investment or the loan. It provides a more accurate measure of the true cost or return on a financial product that involves compounding. The EAR is particularly useful for comparing different financial instruments with varying compounding periods, allowing for a standardized and comparable assessment of their true annual rates. The EAR is calculated using the nominal interest rate and the number of compounding periods per year. Now, both EAR and APR, they are used in the context of expressing the annualized interest rate on financial products, whereas they consider the impact of compounding. Now, while EAR specifically emphasizes the effective annual rate, APR is a broader term that is used to describe the overall annualized cost or return associated with loans, associated with credit cards, and other financial instruments. So the effective annual rate, aka annual percentage yield, which is API, they're usually considered almost the same. So it is the total amount of interest that will be earned at the end of 1 year. Now, interest rates are commonly presented as an effective annual rate, or EAR, or annual percentage yield, like I mentioned, APY, it signifies the total interest earned over 1 year. Now, this quoting method has been consistently employed in your textbook with chapters 3 and 4 utilizing EAR as the discount rate, which is denoted with the R in time value of money calculations. For instance, as you see here, with an EAR of 5%, a $100 investment would grow to, that's $100 times 1 plus R in parentheses, equal $100 times 1.05, which will equal $105. Now, after 2 years, it will grow to $110.25, as you see in this illustration on the slide. Now, that preceding example shows that earning an effective annual rate of 5% for 2 years is equivalent to earning 10.25% in total interest over the entire period. So adjusting the discount rate to different time periods in general, by raising the interest rate factor 1 plus R in parentheses to the appropriate power, we can compute an equivalent interest rate for a longer or shorter time period. So that's $100 times 1 plus R in parentheses to the second power equal $100 times 1.05 in parentheses to the second power equal $110.25. We can apply a similar approach to determine the equivalent interest rate for periods shorter than 1 year. In such instances, we raise the interest rate factor, that's 1 plus R, to the relevant fractional power. For instance, earning 5% interest in 1 year is equivalent to receiving $1.0247. So here you see the formula, 1 plus R in parentheses to the 0.5 or 0.5 power equal 1 plus 1.05 in parentheses to 0.5 power equal $1.0247. So a yearly rate of 5% is equivalent to a rate of 2.47% earned every 6 months. A discount rate of R for 1 period can be converted to equivalent discount rate for N periods. So equivalent N minus period discount rate is equal to 1 plus R in parentheses to the N power minus 1. So when computing present or future values, you should adjust the discount rate to match the time period of the cash flows. Here we have a problem. Suppose your bank account pays interest monthly with an effective annual rate of 6%. What amount of interest will you earn each month? If you have no money in the bank today, how much will you need to save at the end of each month to accumulate $100,000 in 10 years? Here's a plan. We can use equation 5.1 to convert the EAR to a monthly rate, answering the first question. The second question is a future value of an annuity question. It is asking how big a monthly annuity we would have to deposit in order to end up with $100,000 in 10 years. However, in order to solve this problem, we need to write the timeline in terms of monthly periods because our cash flows deposits will be monthly. That is, we can view the savings plan as a monthly annuity with 10 times 12 equal 120 monthly payments. We have the future value of the annuity, which is $100,000. The length of time is 120 months, and we will have the monthly interest rate from the answer to the first part of the question. We can then use the future value of an annuity formula that was in equation 4.6 to solve for the monthly deposit. To execute from equation 5.1, a 6% EAR is equivalent to earning 1.06 in parentheses to the 1/12 power minus 1 equal 0.4868% per month. The exponent in this equation is 1/12 because the period is 1/12 of a year, which is a month. To determine the amount to save each month to reach the goal of $100,000 in 120 months, we must determine the amount C of the monthly payment that will have a future value of $100,000 in 120 months, given an interest rate of 0.4868% per month. Now that we have all of the inputs in terms of months, which is monthly payment, monthly interest rate, and the total number of months, we use the future value of annuity formula from chapter 4 to solve this problem. So in calculating the monthly savings required to achieve a goal of $100,000 in 120 months, what we need to do is to find the monthly payment amount C that, when compounded at an interest rate of 0.4868% per month, what will result in a future value of $100,000 after 120 months. Now, with all inputs standardized in months, meaning monthly payment, monthly interest rate, and total number of months, we apply the future value of annuity formula from chapter 4 to address this computation. So we have future value with annuity in parentheses equals C times 1/R. Then you have in brackets 1 plus R in parentheses to the n power minus 1. So we solve for the payment C using the equivalent monthly interest rate R equal 0.4868% 8%, and N is the 120 months. So in this problem, we would have $615.47 per month. So we can also compute this result using a financial calculator or spreadsheet. Okay, so this is using a financial calculator. So if we save $615.47 per month, and we can earn interest monthly at an effective rate of 6%, we will have $100,000 in 10 years. Notice that the timing in the annuity formula must be consistent for all of the inputs. In this case, we had a monthly deposit, so we needed to convert our interest rate to a monthly interest rate and then use total number of months, 120, instead of years. And then you have the Excel formula at the bottom of the slide. Okay, here's a problem. Suppose your bank account pays interest monthly with an effective annual rate of 5%. What amount of interest will you earn each month? If you have no money in the bank today, how much will you need to save at the end of each month to accumulate $150,000 in 20 years? Here's the plan. We can use equation 5.1 to convert the EAR to a monthly rate, answering the first part of the question. The second part of the question is a future value of annuity question. It is asking how big a monthly annuity we would have to deposit in order to end up with $150,000 in 20 years. However, in order to do this problem, we need to write the timeline in terms of monthly periods because our cash flows, deposits, will be monthly. And here you see the timeline. That is, we can view the savings plan as a monthly annuity with 20 times 12 equal 240 monthly payments. We have the future value of the annuity, which is $150,000. The length of time is 240 months. And we will have the monthly interest rate from the first part of the question. We can then use the future value of annuity formula in 4.6 to solve for the monthly deposit. To execute from equation 5.1, a 5% EAR is equivalent to earning 1.05 in parentheses to the 1/12 power minus 1 equal 0.4075% per month. The exponent in this equation is 1/12 because the period is 1/12 of a year or a month. To execute, here to determine the amount to save each month to reach the goal of $150,000 in 240 months, we must determine the amount C of the monthly payment that will have a future value of $150,000 in 240 months, given an interest rate of 0.4074% per month. Now that we have all of the inputs in terms of months, you have your monthly payment, monthly interest rate, and a total number of months. We use the future value of annuity formula from Chapter 4 to solve this problem. And here's the formula for that. The annuity formula, future value with annuity in parentheses equals C times 1 over R. And in brackets, you have 1 plus R in parentheses to the n power minus 1. We solve for the payment C using the equivalent monthly interest rate R equals 0.4074% and N equal 240 months. So with the equation that you see here, it should equate to, or it has equated to $369.64 per month. $369.64 per month. We can also compute this result using a financial calculator. So in your calculator, you would press 240 for the number, and then you have the I over Y, which is the rate at 0.4074. It will give you that a total $369.64. And at the bottom of the screen, you see the Excel formula to compute it. I prefer using Excel instead of a financial calculator. All right, to evaluate, thus, if we save $369.64 per month, and we can earn interest monthly at an effective annual rate of 5%, we will have $150,000 in 20 years. Notice that the timing in the annuity formula must be consistent for all of the inputs. In this case, we had a monthly deposit, so we needed to convert our interest rate to a monthly interest rate and then use total number of months, which was 240, instead of years. APR indicates the amount of simple interest earned in 1 year. That is the amount of interest without the effect of compounding. Because it does not include the effect of compounding, the APR quote is typically less than the actual amount of interest you will earn. Because the APR does not reflect the true amount you will earn over 1 year, the APR itself cannot be used as a discount rate. Instead, the APR is a way of quoting the actual interest earned each compounding period. So you have interest rate per compounding period equal APR over M. And M is the number of compounding periods per year. Converting an APR to an EAR. Now, once the interest earned per compounding period is computed from equation 5.2, the equivalent interest rate for any other time interval can be computed with equation 5.1. Specifically for EAR to APR conversions, we have the following formula as you see here. It is 1 plus EAR equal 1 plus APR over M to the M power. And of course, M is equal to the number of compounding periods per year. Effective annual rates for a 6% APR with different compounding periods. So to the left, you see the compound interval, which are annual, semi-annual, monthly, and then daily. So the effective annual rate for annual is the 1 plus 0.06 over 1 to the 1 power minus 1, which will give you the 6%. The semi-annual will be the 6.09%. Monthly will be the 6.1678%, and daily it will give you the 6.1831%. Notice here that the exponent is 1, represents annual, semi-annual means 2, twice a year is 2, monthly 12 months, and daily 365 days in a year. Okay, we have a problem here, and this is a problem from the homework assignment. You are considering a car loan with a stated APR of 6% based on monthly compounding. What is the effective annual rate of this loan? Note, be careful not to round any intermediate steps less than 6 decimal places. So what will be the effective annual rate? What will be the effective annual rate for this loan? 6.7%. 6.7%. And how did you arrive at that? This is the equation or the formula. You have the EAR equal 1 plus APR over M in parentheses with MX as the exponent minus 1. That will be the equation or the formula. And to go a step farther, you have the EAR equal 1 plus 0.0600 over 12 in parentheses to the 12th power minus 1. And that's how you arrive or will arrive at 6.7%. And we will stop here.